Considered unbeatable, a 10-meter wall, 2.4 kilometers long, arranged in a giant X along the coast of Tarō, Japan, built to divert tsunamis around the town through channels and river dikes. After tsunamis flattened the town in 1896 and 1933, Tarō built this wall, and engineers from around the world traveled here to study it. On March 11, 2011, none of it was enough. A magnitude 9.0 earthquake shifted a 500-kilometer stretch of the seafloor by several meters in minutes, triggering the tsunami that tore through the coast. Walls built for 8-meter waves met a tsunami of 12 to 15 meters. Nearly 20,000 people died. Tarō, the model town, flooded anyway. So how do you build a wall that survives what the world's best example couldn't? Join Breakthrough Engineering as we uncover the answer. The X wasn't decoration. Taro's wall was actually two connected sections, one facing the sea, one facing the land, designed so an incoming tsunami would be steered sideways through channels and river dikes and pushed around the town instead of straight through it. It worked. When a tsunami triggered by Chile's 1960 earthquake reached Tarō, the wall held and not a single life was lost. 4 tectonic plates meet beneath Japan. Over 500 earthquakes strike the country every year, and no nation on Earth has spent more time preparing for tsunamis. It still wasn't enough. More than 120,000 homes were destroyed in 2011, and the disaster triggered the Fukushima nuclear catastrophe. Taro's failure told engineers something the statistics couldn't. This wasn't a failure of the idea of seawalls. Japan had been building them for over a century. This was a failure of scale. Walls built for the tsunami they expected, not the one that actually came. So what would it actually take to build for the one that did? Japan's answer wasn't a taller version of the same wall. It was $12 billion and roughly 400 kilometers of coastline along Tohoku, rebuilt as a single interlocking system. Seawalls, dikes, floodgates, breakwaters, drainage networks, coastal forests, and elevated evacuation roads, all working together. Tens of thousands of engineers, construction workers, and geotechnical specialists spent 5 to 7 years on it. And the first thing they had to fix wasn't concrete. It was a misunderstanding. A tsunami doesn't look like the movies. There's no towering wave that crashes and breaks. It looks like the sea level rising at terrifying speed, an unbroken wall of water that keeps climbing and simply doesn't stop. That single fact changes the entire engineering problem. A wall doesn't need to absorb an impact. It needs to hold against pressure that keeps building, second by second. Here's the single most important idea behind the entire project. The wall isn't built to stop a tsunami. It's built to buy people time. Every extra minute is another minute someone can use to reach higher ground. And that one idea shapes every design choice that follows. The new walls reach 14.7 meters high, but that number hides the real engineering. Their foundations run up to 25 meters deep, deeper than an 8-story building, completely buried underground. And it has to survive 2 disasters back to back. First, a magnitude 9 earthquake, then, minutes later, the tsunami itself. The real danger was never the pressure of the water, it's what happens underneath. If water scours away the soil beneath a wall, the entire structure loses its footing and goes down. So in front of every wall sit tetrapods, dolos blocks, and riprap stone, breaking the wave's energy before it ever reaches the foundation. The philosophy shifted too. These walls are now allowed to be overtopped. They just aren't allowed to collapse. That means the back side needed protecting as much as the front. Water pouring over the crest can erode a wall from behind just as easily as the sea attacks it from the front. Between every layer, engineers laid geotextiles, sheets that stop the fill material from being washed out from inside the wall, a lesson learned directly from watching the old walls fail. But even the strongest wall has gaps. Harbors still have to function. So every harbor opening gets its own hydraulic floodgate. Some drop straight down, a steel panel hanging between two concrete towers that lowers on alarm. Others rise up from the sea floor, lying flat so ships can pass over them until an alarm lifts them into place to seal the gap. Every opening is a weak point, and every weak point gets its own defense. On top of the wall runs something the public never uses, a technical inspection road with concrete slabs, railings, access stairs, and dedicated safety systems, so crews can check the structure after every storm and earthquake. But even a wall this strong was never meant to stand alone. The wall was never meant to work alone. Behind it, a coastal forest that stabilizes soil, slows the wind, and catches floating debris. An elevated road that pulls triple duty as an evacuation route, a barrier against incoming water, and an access path for rescue crews. And an early warning system pointing the way toward higher ground. Each piece of infrastructure earns its place doing several jobs at once. Japan calls it layered defense. Against the smaller tsunamis, the kind that hit every 50 to 160 years, the wall alone is enough to stop them outright. Against the rare, devastating ones like 2011, which strike only every few hundred to 1,000 years, the rest of the system becomes decisive. Early warning, evacuation plans, and a population that knows exactly what to do. Simulations show the system cuts tsunami impact forces by 30 to 50%, buying several extra minutes of evacuation time in a typical event. That sounds small. It's the difference that saves tens of thousands of lives. But not everyone welcomed it. In places, these walls stand nearly 4 stories tall, and they don't just block water, they block the ocean itself. Fishing families who've lived by the sea for generations say it feels like living behind bars, the horizon gone behind gray concrete. Others look at the same wall and see a promise. 2011 will not happen again. Some towns went further still, moving entire neighborhoods uphill and banning new construction near the water. A decision that reshaped coastal life here for good. And there's one more twist. Build a wall too high, and it starts to behave like a dam. If it ever fails, all that held-back water releases at once, with even greater force than before. Height and stability have to be balanced with precision. A taller wall isn't automatically a safer one. $12 billion, 400 kilometers of coastline, 7 years of work. Built not to defeat the ocean, but to buy the people living beside it a few more minutes when it matters most. Would you want to live behind a wall like this, knowing what it's built to survive? Let us know in the comments, and if you want to keep exploring the world's greatest feats of engineering, join Breakthrough Engineering for the next one.